Okay, hi everyone, welcome back. So it's another data analysis video. Again, I'm using Jupyter Notebooks. I'm doing the analysis using Python and the different software libraries available in Python. So in previous videos, I've kind of created a series of videos which have worked through how to clean and tidy up your data so it's in some sort of reasonable format so you can run some sort of statistical tests or analysis on it. And I've also created a series of videos showing you how to create different visualization of data and variables so that you can explore your data. So assuming maybe you've done that, perhaps then you might want to move on and conduct some sort of statistical test, some sort of inferential statistical test, or test some sort of hypothesis. So this is the first of a kind of series of videos where I'm going to focus on what we would consider to be the classical statistical hypothesis testing types of analysis. So what we'd often refer to as frequentist statistical analyses, where we're looking at whether there are differences between groups and statistical significance and stuff like that. And I'm going to start by, in this video, I'm going to start with the t-test. So comparing two groups or conditions, see if there's a significant difference between the means of those groups. And then I'll move on and conduct some other different tests, demonstrate how to run those. So I'm kind of starting with the type of stuff that people commonly learn when they do undergraduate statistics in psychology or other disciplines where you have to learn data analysis. And one of the places people often start is by kind of learning the t-test, learning how to test, see if there's a difference between two groups. And what I'm going to do in this video is I'm going to start with the one sample t-test, which is kind of I don't think it's something that has a great deal of use. The idea with one sample t-test is you have some sort of sample group mean, and you're looking to see if it's different from some hypothetical population mean. Often you wouldn't know what that population mean is, so you just assume the difference is that is between your group and the population mean is 0, or if it's not 0, then it could be statistically significantly different. But what I'll do is I'll in this video I'll demonstrate how to run a one sample t-test on some made up data, and then in the next couple of videos I'll then run an independent groups test, and then a repeated measures, or sometimes referred to as a paired samples t-test. Okay, so to get started, I'm going to import some libraries, some software libraries. I'm going to start with NumPy, which I'll import as NP, pandas as PD. I'm going to import scipy.stats as stats, matplotlib.pyplot as plt, and I'm going to import the math module from the Python base environment in case I want to kind of manually calculate anything such as standard deviation. So the main thing I'm going to use here is NumPy and the scipy stats library. So I've not previously, I don't think I've recorded many videos where I've used scipy. Scipy is really good. It's got really good kind of software library for running different types of statistical tests. And that includes the tests that I'm going to use it for today. So if I run this first cell, I'll import those. You'll notice that there's this kind of this percent sign matplotlib inline. This is kind of what it's often referred to, I think, as a magic command when you're using these Jupyter notebooks. And I used to use it quite frequently, but less so now. And I think the idea behind it was it's when you create plots, say in Jupyter Notebook, it used to be, I think, the case that they would pop up as separate windows, and using this particular command would like embed them within the notebook. It seems to me that the default is that they're embedded within the notebook, so I'm not sure it's something that's that commonly used anymore. But anyway, that's what that is, in case anyone looking at it was wondering what it was for. So first of all, I'm going to create some made up dummy data to use an example. So this data is going to be about mean voting age for a population and for a sample from the county of Yorkshire. So that's where I'm from originally. So I kind of did this to keep it sort of relevant, I suppose, or something that people can understand if you're in the UK. So what I'm going to do is I'm going to create a load of random data for the population with set parameters. So we have a certain type of a population mean of roughly a certain value, and then I'm going to generate a kind of much smaller sample of data, randomly generated data, which will give us kind of the mean age of voters from Yorkshire. And I've set this up deliberately so they'll be different from each other, so we can see how a statistical test kind of works and gives us a significant result if we have a difference. Don't worry too much about the code in this cell. I will create another video where I'll demonstrate how to simulate data, generate random data, so you can use it to test different types of analysis. I'll create another video that sort of shows that. But all I'm doing here is basically I'm using the .rvs, which is the scipy random variance method, to create a couple of large samples, which I'm going to save as the population, and then I'm going to join them together as an object called population ages. I'm specifying kind of the lowest value and this shape value, which is essentially kind of like the mean. And I'm using a Poisson distribution, so that's a discrete probability distribution that is often used to model the number of events that occur in a given period of time. So it might be a useful distribution for modeling kind of voting age, because I guess we'd expect fewer events as people's age increases due to mortality and people dying. And also when we're recording voter ages, we're not doing it on a continuous scale, we're doing it on a discrete scale, usually just 18, 19, 20, whatever their integer value is of their age. They don't give you that with infinite precision. So I'm doing a similar sort of thing for a much smaller sample of just 50 people from supposedly from Yorkshire. If I run this cell, I'm just going to print out, I'm using the .mean method to work out what the means are for these. So we can see that for the population, we've got a mean voter age of 43, and for Yorkshire, from our sample, we've got a mean voter age of 39.26. So it says voters seem to be younger in Yorkshire, but the question we're asking here is that difference statistically significant? Are voters in Yorkshire younger than the population on the whole? Often you wouldn't, if you were doing this, you wouldn't actually have the population mean value that you were interested in, but you need it to conduct this one sample t-test method using scipy. You need some sort of value to put in there. So let's conduct the actual test. So to conduct an inferential statistical test at the 95% confidence level, see if the mean age for Yorkshire voters differs significantly from the mean age of voters in the population, what I'm going to use is the scipy stats.ttest_1samp method. So you can see that here I'm calling stats, which is what I imported the scipy stats as, saved it as, that's the nickname I gave it. I'm going .ttest_1samp. And then in these parentheses, I've got to pass the arguments, and the arguments are the sample data. So A is one of the arguments you have to specify, which is the data you want to use, and that's the sample data for Yorks. If you see here, from these kind of two samples that generate, I've got York's ages data, and that's what I'm passing in as the data for the sample, this particular object here, which is kind of a numpy array of all these samples of 50 samples of ages. Okay, and then I've got to specify the population mean that we're comparing it against. And to do that, I'm just using the population ages, but the actual mean value of it. So the population ages.mean, I'm taking that. So this second parameter here is basically this value 43. So it could be an array, or it could be kind of an individual, like an individual value. So let's run this particular cell. And what you see is you get the output, t-test1samp result, and in parentheses it gives you the t-test statistic, which in this case is -2.57 if we round it to 2 decimal places, and it gives you p-value of 0.013. So what we're seeing here is that although 39 and 43 are not that far apart, given the size of our sample, given the size that we're comparing it to, and the degrees of freedom we're using, what this is telling us is that voters in Yorkshire are significantly younger than the population mean. Okay, and it's significant at the 0.013 level. So this is assuming by default a significance level of alpha equal to 0.05. So we are, it's commonly used as a convention in social sciences and a number of other disciplines that if the null hypothesis is true and there isn't a significant difference between our sample group mean and the population mean, then if there's a probability of lower than 0.05 of seeing a difference this big, we reject the null hypothesis and we accept that there is some sort of statistically significant difference between our sample mean and the population mean. And that's what this is telling us. So what this is telling us is if there isn't a difference between mean voter age in Yorkshire compared to the population, then we'd only expect to see a difference this big, albeit it's only like 3, 4, about 1% of the time. Okay, right, so we've got our t statistic, we've got our p-value, we've got a significant test. So what we know is the t-value lies outside the 95% confidence intervals for the t distribution based on our population, and we can check this by getting quantiles for the top and bottom 2.5% tails of the distribution. So if we're not making a directional prediction here as to we expect it to be younger, older, then we're splitting the significance across the two tails, and like the 2.5% in the upper part of the tail, 2.5% in the bottom part. So we can obtain this by using this method called stats.t.ppf, which stands for percentage point function, and I've passed it a couple of arguments. The arguments are q, which are the quantiles, and I've specified 0.025, so that's the lowest 2.5% of values. And I've also passed the degrees of freedom. So for our sample, in this case, degrees of freedom of 49, we generate 50 samples for our Yorkshire radius sample group. And if we do that, what we see is we've got like this lower value for the t-value. So if it's negative 2.00957, various other numbers, so I could have specified that we want this to 2 decimal places. But if we've got a value that's lower than this, so more extreme than this, a t-value, then we know it's kind of within that it's beyond that bottom 2.5%, and we kind of already know this because it's statistically significant. So our t-value is negative 2.57, and that's smaller than this value. So we kind of what we know is, and we can look at our mean scores to sell this. We know that the sample mean is smaller than the population's mean, so we kind of know that it is significantly kind of beyond this cutoff value that was given to us by a percentage point. It's smaller than the bottom 2.5%. Or it's a smaller value that is like smaller than this. We sort of knew that anyway from this, but that can be useful. We can generate the opposite, so for the top 2.5% as well. So, and to do that, we use the same t or ppf percentage point function, but we'd specify the quantile as 0.975. So that gives us the top 2.5. What t-value is the cutoff for the top 2.5%, and that would be kind of the kind of opposite of that. We know that we didn't really need to do that for this particular analysis because we're only comparing one sample to the population here. and we know that the sample was smaller than the population. If these had been the other way around, then I guess what we'd be looking at is, like the sample being significantly above. But that's just to demonstrate that you can kind of look at what the cutoff value is, the kind of confidence intervals for our t-values, essentially. Right, so an alternative way to get the p-value is using our t-value as the argument and what we could call the stats.t.cdf, so cumulative density function method. And what we do is we're going to use stats.t.cdf, and then we're passing it as an argument, as I said, as we've got to pass it this x argument in parentheses. And note that what I've done here is I've passed our actual t statistic here, rounded to like 4 decimal places, so it's reasonably precise. So you notice that this is the same value as our t statistic just there, and I've passed the degrees of freedom. I'm also, outside of the actual parentheses, I've got this asterisk 2, so I'm multiplying the CDF by 2 because we did a two-tailed t-test essentially. So we don't want to we've not made a directional prediction, and we don't want to kind of end up with a type 1 error, something like that. So this is kind of making it clear that we should be splitting it across the two tails essentially. And if we run that, what we will get essentially is our p-value, the same value as our p-value above, or a close approximation of it. Okay, so it's not exactly the same, but it's about 1.3%. So what this is telling us is the probability of getting this difference in means by chance, if there is no difference between our sample and the population, is about 1.3%. So it's highly unlikely. We kind of knew that already just from the test statistic, but these are kind of just other ways to examine what we're looking at. So if we wanted to construct an actual 95% confidence interval for our sample, because we know, because we got a significant test, it shouldn't, the 95% confidence interval for our sample mean it shouldn't capture the population mean. The population mean should be more extreme, should be higher than the confidence intervals around our group mean. But we can work that out. And what I've done here is I've created basically sigma, which is effectively the standard error. So I've taken the Yorkshire ages, taken the standard deviation, and then I've divided it by the square root of the sample size. Okay, and then I'm going to use this stats.t.interval, so asking for the confidence interval, and I've specified 0.95, so the 95% confidence interval. The second argument I'm giving it is the degrees of freedom. I'm saying use as the location the mean age for Yorkshire, and use as the scale, standard error, the sigma object that we created above here. Okay, so if we do that, that gives us the upper and lower bounds of the kind of 95% confidence interval for our Yorkshire ages group. So it goes from 36 to 42, and the mean, as we know above, was about 39. Okay, so we also know, if we look at that our population mean is higher, is bigger than this. Okay, so we've constructed, there it is, 43, so it sits above that. So we've constructed confidence intervals there, and we could report those as well. All right, last thing I'll do is I'll kind of demonstrate this again, but this time we'll change the confidence interval to like a 90. We want to say we wanted a strict significance level criterion. We could adjust this alpha criterion, this alpha level, the first argument of our interval when constructing this. And in this case, what I'll do is I'll set alpha. I've kind of written it in a different way here. I didn't put alpha equals there. I just specified the 0.95 value. But here I've put alpha equals 0.99. So I'm basically saying we're only going to accept a statistically significant difference if there's kind of like a 1% or less chance of seeing that difference. And we know that it's slightly above 1%. So if I run that this time, what you should see is we've got confidence intervals from 35.41 to 43.11, which obviously now this upper confidence interval here would include this population mean. So our ages, so our Yorkshire ages group, our mean voter age for Yorkshire is significantly different from the population mean at the 0.95% confidence level, but not if we use a stricter criterion and set that at 0.99. So the 5% level is significant, but the 1% level it is not. Okay, so that's the one sample t-test. As I said before, I can't say I've ever really used a one sample t-test for anything, but that's how you kind of run that using scipy, and obtain some other stats that can be useful in interpreting what's going on and creating confidence intervals in case you want to report them. In the next video, I'll do an independent groups two sample t-test, demonstrate how to do that. This example that I used here was kind of made up data. Hopefully that was useful, but you can see I've used scipy here. There are other software libraries that are good for running this type of test, and I will demonstrate some of those as kind of go along. Okay, thank you.